So here is the circuit here. So I'm using microcap. I have a simple inverting amplifier, right? Inverting amplifier is given. And this is not an ideal op-amp now. This is a realistic op-amp model that is being used. And I've given 1 millivolt here. So what do you expect? What do you expect now? If it were ideal op-amp, you would have expected 1 millivolt multiplied by 100. So you would expect minus 100 millivolt. Correct? Okay. Now, in light of the experiment that you have done with all the non-idealities, what would you expect? Would you expect something different from 100 millivolt? Look at all the details are here. Before I run the simulation, what would you expect? All right. So how do I run the simulation, by the way, here? What do I do now? I want to find out what the output voltage is, right? So how do I find that out? Analysis and do what? Huh? Dynamic DC, right? So let's do the dynamic DC and let's see what it gives. Right? So let's see. All right. 13.87 millivolt. Right? Ideal op-amp, we expected minus 100 and now it's giving me 13.7, and not only it's not giving me minus 100, it's giving me plus. Right? It's giving me plus. Okay. Now I want you to suggest how can I step by step bring it, what changes should I make to my op-amp and step by step bring this to minus 100 millivolt. Obviously there are non-idealities in the op-amp, right? Which is causing it to deviate in this significant manner. Now you know all the non-idealities. Which one comes first in your mind? Which one should I fix first? Offset? Okay, so I'll double click on this. I go and look at offset. So offset would be right at the end. Offset voltage here is 1 millivolt. Right? So it's 1 millivolt is a very, and I guess that's the value that you guys measured also. Roughly around 1 millivolt, 0.5 millivolt and all that. So one can see that 1 millivolt is causing a problem. So let me make it very small. Let me make it 1 pico. 1 pico volt. All right. So let's see. Okay. So it came, it was causing a lot of problems. It's come to minus, but I still have minus 85. I want minus very close to 100. So what should I do now? So offset voltage we have taken care of, right? 1 pico is like negligible. Okay, what shall I do next? Huh? Bias current. How is bias current distorting it? Where do you think bias current is flowing? How? Let's see the bias current. So the currents, what do I expect? How much current to flow here? 1 milli divided by 1K. So it is 1 micro, right? And this we expect 1 micro to flow through 100K here. How much is actually flowing? Let's do this here. So lesser current is flowing, right? Because this current now that you see here, part of it is flowing into the op-amp here. So what you're saying is I should go ahead and edit the bias current. All right, let's do that. So bias current is 80 nano. Let me put it to 80 femto, right? So let's make it very small, 80 femto. They also have something called I offset, which means that the two bias currents are not the same. So let me also put some femto, right? All right. Okay, so let's see where our output voltage has gone. Minus 97.834. I still don't have minus 100. So bias currents have eliminated. Offset voltage sort of eliminated. What else should I eliminate now? Offset null is the pins are there so that, so here I'm just going and editing the model parameters, right? So in a real op-amp, how do you make it 1 pico or whatever? So it's, you using a potentiometer, you can adjust and sort of cancel it. So in a real device, there is a means provided for you to tune the mismatches and make it 0. Right? So now minus 97.834. How do I get it to 0? So two of the non-idealities you have identified, offset voltage, bias currents, we have gotten rid of. Is DC. Is DC. So what shall I do now? I wanted at least to go to minus 99 point something, right? What changes should I make? What changes should I make? Okay, so normally when you say ideal op-amp, what are the things that you've learned about ideal op-amp? When did you say op-amp is ideal? In fact, when you were first taught op-amps, you were probably not told about offset voltage and bias currents and all that. You were told something else. Open loop gain? Like going very high. And what else? Huh? Input resistance very high, output resistance very low. So let's go and see gain. He's saying, let me make it very high. Right now, can you see the gain? 200K. So 2 into 10 power 5 is fairly large, but if you want, I can make it large. I can make it instead of 200K, 200 meg. Right? So I artificially make it like that. Did it make much difference? Not that much. So 200K was already very large. So it's not making that much difference. What else? Input resistance. Did you guys see input resistance anywhere? In fact, it doesn't mention input resistance, I think, at all. It mentions output resistance. There's no input resistance at all in the parameters, which means it's already taking it as infinite. It's assuming it as infinite. Already assuming it to be infinite.
If input resistance is infinite and open loop gain is also very high, then virtual ground component should be strictly cold, but it is not.
Yes, still there is a 20 microvolt appearing here. What else could be wrong? Huh? Which level? Oh, level. Okay, what is this level here? Is the complexity of the model. So what he's saying is change the level. In fact, what levels does it allow? Level 1 is I can make it ideal. I can make it ideal, so it will become ideal op-amp. And we know what to expect in an ideal op-amp. Right? It will become this thing here. So what we are trying, we will not change the level here. What we are trying to identify is which parameter is making a difference. Right? So we've identified some of them. Which one is making a difference here? Huh? Yes. CMRR. It's also a difference amplifier. Let's see if CMRR makes a difference here. CMRR, see 31.62K. Let's also make it meg. Right? 99.9999. So that's where it's gone. Right? So you need high gain, you need high CMRR, you need negligible offset voltage, and you're almost close to ideal values here. Right? So that's how you edit it and you make it ideal. Right? But suppose I do this now and I go to my next circuit here. It's the same amplifier, 1K, 100K, same amplifier. And same edited parameters. I've made, you go here and you see 200 meg, everything is the same, right? I've edited everything. But now what I do is, I look at his gain, not at DC, but at let's say some other value here. Analysis, let's do AC, dynamic AC. Alright, dynamic AC. And it says at what frequency do you want? So let me look at it at 1K. 1K. And at 1K, I'm getting 99.497, which is pretty good, right? Okay, dynamic AC limits. Let's run it at, say, 100K. 9.8. So What has happened now? Gain is so this, when you're doing AC analysis, what does it assume? The input is 1 volt magnitude, and therefore is giving you the output in terms of that. Because in AC is a small signal analysis, what matters is the ratio. Okay, so it says gain is 9.867. So what has happened is the gain is, even though note, now this is very interesting, even though gain is how much? 2 into 10 to the power 8. Gain is very high. But then why is it no longer virtual ground then? Because gain is a very strong function of frequency also. So in fact, gain drops very rapidly. So even though you may have, so what it is showing you is, even though you may have a circuit which is working fine at lower frequencies, where this node acts as a virtual ground, because at lower frequencies the gain is very high, at higher frequencies the gain drops and is no longer virtual ground. Right? So even when you have the DC gain, which is very, very high, you find the virtual ground property is violated here, and you don't get the right answer here. Okay. So these are, so here I could easily edit all the non-idealities and got rid of it. Okay. But in real life, let's look at this one here. In real life, suppose I have a requirement where, let me get rid of this, where I have a requirement of measuring a signal which is very small. Let's say this 1 millivolt that I've put here is actually coming from, let's say, a temperature sensor. Okay, I have a temperature sensor and it gives me a voltage of 1 millivolt, or it is coming from a pressure sensor, and I want to measure this voltage here. So I have a requirement of measuring very small voltage here, 1 millivolt. Now, when I measure, as I said, I'm expecting 100K, and what I end up getting is, now let me put back all the normal, in this case, all my values are the normal parameters here. So I'm expecting, so I'm expecting that my 1 millivolt signal will get multiplied by a factor of 100, and by measuring the output voltage and by knowing the gain of the amplifier, I'll be able to infer what is the sensor voltage, right? So that's why I'm building the amplifier. But then what I'm getting is I'm getting this value here, and by measuring this value here, I cannot infer the value of this one properly, because this is, if I just simply divide by the gain, then I'll not get the right value here. So the issue is, now you will encounter situations like this, right, where you want to amplify a very small voltage like this here, but then all the opamp non-idealities are coming into picture and you're not able to measure. And as I said, you can't just go now, and one way is, you may think, well, let me try and, somebody said null the offset voltage here, but it's a difficult process. And if let's say you are a manufacturer and you're making 100,000, 1 lakh such amplifiers and selling it, you can't really go on each one of them and sort of tune it and make it offset voltage negligible. You can't do that. It's too costly to take each one of them and then tune it and make it this thing here. Another problem is the fact that it's too costly. What would happen is, offset voltage is a function of temperature. So you may tune it and make offset voltage negligible, let's say at room temperature, and then when it goes to the field outside at 50-degree, offset voltage is something else, and your tuning is no longer fine. Or you take it into a very low temperature environment, again, offset voltages become different, and therefore it's no longer tuned out. Right? So it's not always possible to tune it. So now the issue is, let's say I have offset voltage, and I would still like to measure this voltage in a reliable manner. What do I do? Here? I add the voltage here? And to do what? That's what I'm saying, tuning. Tuning is the same thing. You may be able to cancel the effects of offset voltage. Let's say we are sitting here at room temperature. What will happen at 50 degrees? Now you have sold the amplifier. It's in the hands of the user. He's not going to look at it and tune it, right? He wants to measure the temperature by measuring this voltage here. So how do I still design? So these non-idealities you will still find. How do I still design an amplifier, measure my voltage here without offset voltage coming into picture. Increase the input and decrease the output. So now, how do I increase the temperature?
Instead of 1 volt, if we make 10 volt and divide the output.
Which one? Which one 1 volt? This? But this is coming from my sensor. How do I increase the temperature? It's not under my control. Can't increase the temperature, decrease the temperature. I can't do that. Or let's say this is a sensor embedded in a building which is measuring the pressure. So I can't really change. Right? So what do I do? Maybe you're on right track though. What was the idea behind?
Because we created that because we offered as fixed.
Okay.
It will become negligible with respect to the input increase.
Not really, but you're on right track. What he is onto, what he's saying is offset voltage is probably constant. Offset voltage, it may change. We are saying offset voltage does change, but it changes over a longer time scale if the temperature changes or something like that, over a longer time scale. If I'm measuring over a very short time scale, let's say over a second or 2 seconds, offset voltage is not going to change. It's a constant. But our problem is this is also a constant. And the two constants are the same. Yes.
Apply some bias.
Where? At this point?
Add some voltage to it so that.
Okay, then what will happen?
It becomes like it becomes with respect to any other.
But then I want to measure this, right? Then I'll be measuring what you attach.
Yes, and some small changes are reflected. Small changes when they are affected by the offset voltage.
What you are saying is I attach a voltage here at this point, and a variable voltage.
Instead of ground, we make it
Make it. Look at the gain here. If you let's do that. So what you are saying is right now this is what it is. From this I cannot tell anything about this, right? Now if you add something, okay, how much should I add? Let's add. Let's add here. How much do you want me to add? I can add a DC voltage, whatever DC you want, I can add. Let's say what? 10 millivolt? 20 millivolt? Something larger than what exists? Is that what you're saying? Something larger than that? Let's add 10 millivolt. Okay. What can I say? From now, all that you have is you're measuring the output voltage 231. You've added 10 millivolt. What can you infer? Can you see? My goal is by measuring the output, I have to infer this, right? Can I infer the correct value of this one?
So we increase it from 10 to some hundreds, like 500.
This one? We increase it more?
500.
How will that help? That's what I'm trying to understand. How do I 500 milli? Okay, fine. It's saturated now. It's gone to saturation because it's very large. So let's decrease it to maybe 250. 250. It's still saturated. 200. Well, it's saturating. 20. 50. Okay. You can increase it. I get a large value. I can't infer. All that you could infer is from this, if you're making this much larger than this, then by the gain, all that you'll infer is what value have I attached. You are measuring this. You'll end up measuring this which you already know, not the one which is here. So in fact, you're creating sort of more problem because you want to measure a small value here. And in addition to that, you are adding another big one. So it's creating more of a problem rather than a solution. But what I would still say is you guys are on the right track in the sense that keep in mind that the key point is your offset voltage which is causing a problem. Offset voltage, bias currents, all of that are constants. They're not changing. While this one is also not changing, right? Your signal is also not changing and your offset voltage is also not changing. Now somebody said, can I make my signal time varying? Can I make this time varying? So time varying means, are you seeing the strategy? The two, right now, this is also DC and all the offset voltages, everything is a DC and they're mixed up. They're mixed up. To separate them, I must create a difference between my signal and my unwanted component. Some difference I must create. And the difference that I'm trying to think of is, can I make one of them time varying and the other one will not be time varying? And how can I make it time varying? What about this one? How do I make this time varying? See, what is coming from my sensor is fixed. I can't change my sensor. I can't change the temperature. But I could still change what goes into my circuit. I think that's what all of you were trying to do by adding something, changing what goes into my amplifier. How do I change that? Huh? This is fixed. I'm not changing this. But what I'm saying is the signal which goes into my amplifier becomes time varying. Changing a resistance in a time variable is not easy, right? What can I do? Something very simple. Huh? Don't attach a source. I want to make this signal time varying. Don't attach a source. Then you're adding another source. You will be measuring that source. You don't want to do that. Attach a switch. Suppose I attach a switch in series, right? And switch, I close, I open, I close, I open. Then what happens to my signal which goes into my amplifier? Does it become time varying? Right? It becomes time varying, but if now, okay, so what you're saying is let's put a switch here. Then my signal is either going or not going. Okay? Now, for the time being, let's see the following here. Let me remove this. Okay? Let me remove this for a moment here. If my signal, so what you want is your signal to become time varying. Alright? Suppose I take here and I put ground. Right? Or I open. Right now, let's say the switch is open. Right? How much is the value here? 17.483. What is this value coming due to? Because of the opamp, offset voltage, bias currents and all that. When you close the switch, what will go here? 1 millivolt. Right? But let's use superposition principle. Suppose I close the switch and there's nothing here. There's nothing that goes here. What would you expect? What do you want at the output then? The time varying signal should be? Alright, so see what I'm saying is, suppose I make this 0, and see your strategy relies on, is on the following, right? That when I open the switch, I have a certain output voltage. And that is only because of the offset voltage. When I close the switch, then I have due to this one. But due to the op-amp, it should not change. But are you seeing that it changes? Right now, I have no signal. When the switch is closed, how much is the voltage here? 868. When I open the switch, it is 17.4. The op-amp's contribution is also changing with time as I open and close the switch. And why is that happening? Because when you open the switch, what is the circuit that I have? This part is redundant. And whatever is the offset voltage here, the same value goes here and it appears over here, right? Something like that. But when the switch is closed, then what do I have? It acts like an amplifier. The offset voltage is here and this acts as an amplifier. And so the offset's contribution also is changing with time. So how can I make the contribution of the offset voltage independent of time? Yes. So okay, I understand. What he's saying is when you open this switch, what you do is you have another switch which closes it. Is that? So that the op-amp, so what we are talking about is that as you open this, right? As you open this, let's remove it. But then at the same time, you close another switch here so that it remains at the same value. The op-amp's contribution does not change. Two switches, right? So op-amp's contribution stays stable at 868 or whatever. And signal, now when you close the switch, the signal will either go or not go. And therefore the contribution of the signal will become time varying. And the op-amp's contribution would be constant. Right? So this is exactly what I did. So let me show you how one can implement this. It's here. Can you see this all? This is what is being done here. This is not very clear. So we have put two switches. You can let me first remove this here. We have put two switches here. One switch to connect this on or off, and the other switch here up. So when I'm opening this particular switch, I'm still taking this and connecting it to ground. So I'm maintaining this point, that this point does not, the op-amp's contribution remains the same by connecting two switches, right? So now let me show you that if I run these two switches, so when I open this switch is closed. And when I close this switch is open. So these are like non-overlapping switches. And so op-amp's contribution remains the same. And the signal's contribution becomes time varying, right? So if I do that, let me now run transient analysis and see what happens. Can you see what happened? Let me look at here, especially this node. This node is this node is 12. Now, why have I added this capacitor in this? Because I want the time varying signal to pass through, and the DC, the op-amp's contribution would be blocked by the capacitor, and the time varying signal will pass through. So let me look at node number 12. Analysis transient, and let me just plot node number 12 and and let's run it. Can you see now very close to what did I expect the op-amp's contribution should be? How much? 1 millivolt multiplied by 100. So we were expecting minus 100 to come in here. And what you see here is very close to minus 100 here. This one here. The capacitors and all that one has to adjust properly to get a proper value. So now the op-amp's contribution has been blocked by the capacitor. All that offset voltage and bias currents and all that, what do they contribute? They contribute only a DC value. And that has been blocked by the capacitor. The signal through these switches has been made time varying. And the signal then travels through and appears over here. So that's why you can see almost like if I go and look at that, 96.83. We expected minus 100 millivolt and we're getting 96.83. To verify that it's indeed signal, what you could do is you could double this. 2 millivolt, I should expect it to double here. It did sort of double. Minus 192. So I'm now measuring the signal. So that's how one is getting rid of the effects of, even though my offset voltage is there, bias currents are there, all of those things are there. I've not eliminated them, but I've eliminated its effect on my signal here. I've made the signal time varying. This is a very powerful technique. By adding this switches and all that, we have made what we call as a chopper amplifier. So I'm taking my signal and I'm chopping it up. These switches are chopping my signal here. It's making it time varying, and then time varying signal then goes through, and I'm able to measure it. And my DC, offset voltage and all that are all DC. They're all blocked. Right? So that's how you get rid of it. But then that's only, I'll not go into the details, but that's only part of the story. The other part, you must be wondering, what is this here? Right? Now, we didn't do this as part of our experiment, but suppose you, in real life, what you do is you take an amplifier and you don't give it any input here. You make this ground and you look at it in the oscilloscope, especially if the amplifier is higher gain. You look at it, the oscilloscope in the AC mode, you'll see noise. The op-amp is a source of noise. So what I'm doing is to simulate the noise, I'm attaching noise here. All right. So microcap allows you to attach a noise source. So let me edit it right now. What it will do is it will add noise, which will change every 10 microsecond. Let me put this amplitude as, 1 millivolt here. So let's see what happens if I add noise here. Let's run. So now, we were using this value to infer the what my signal is. Now my signal is noisy, right? My signal is noisy. So let me add more noise here to make it more interesting. 1 milli. Let me add 10 here, 10 milli, just to exaggerate the effect. Now analysis transient. Let's run. Whoa. So if you're really measuring very weak signal, right, it's going to be immersed noise. So I've gotten rid of the effects of offset voltage and everything because those were time independent. Those were DC. But my noise is time varying. And this is what I may see on the oscilloscope here. So now how do I get my signal? What do I do? Huh? Okay. Low pass filter. So let's make it 100. Cutoff frequency will become even lower. Okay, that's the strategy. You know what it will do? Because your signal also has a frequency. So it's attenuating the signal also and sort of noise also. Both are getting attenuated. So now the issue becomes, okay, we have gotten rid of offset voltage, bias currents and all of that by chopping. But then this chopper also, there is a noise here associated with it. What do I do with the noise now? If the noise starts to bother you, how do I get rid of that? Noise is unpredictable. by definition is random. It's not predictable. So what you're saying is add noise here also, but the noise, the two noises are not going to be the same. Where? I do what? Here. But noise is actually not coming from, I've not attached a noise. Noise is coming from inside the op-amp. I can't go inside the op-amp and attach a capacitor. It's coming from inside. Where from inside? All the transistors are sources of noise. Every transistor is a source of noise. Band pass filter. So what you're saying is you chop it up at some frequency and use a very narrow band pass filter, which will preserve the signal and sort of get rid of the noise, right? So that's the strategy. Filtering was what is being suggested. So filtering, you can do it, but making very narrow band pass filter becomes an issue. That's the strategy. You're right. Absolutely right. Make a band pass filter around the signal frequency and do that. But here is a very interesting solution which I'm not showing. Your signal is, we are on the right track. The signal is at some, let's say we are chopping it up at a frequency of 1 kilohertz, right? So chopping frequency is very precisely defined as 1 kilohertz. Noise is spread over large frequency. So there is a difference between signal and noise. One is spread over a large frequency, the other one is one single frequency, which is F. Can I take advantage of that? See, in all this separation of signal and noise, you have to look for a difference. Difference between what you want and difference and what is unwanted. And you have to exploit the difference. Yep.
So if somehow you can give a delay to the output and multiply those two, maybe that means there is an
delay and multiply, I guess, autocorrelation or something. Is that what you're saying? So I don't have it here, but suppose I do the following. What we are saying is, I have a signal, I have a Y, which is signal, which is, let's say, of course, I'm giving I'm giving a square wave, right? I'm chopping it up like this. But the square wave has what? Has a frequency at F and 2F naught and all the multiple values, right? So I know, let me just look at it. Right now I'm saying the signal has a frequency component which is sine omega t. Plus it will have A naught, whatever, B naught, sine 2 omega t and some higher values, fine? Right, some higher values. Plus I have noise. So what we do is, suppose I take this sig y and I multiply y by sine omega t. I know, do I know omega precisely? Because I'm chopping it up. So I know omega precisely. So whatever is the signal that is coming here at this point, right? The signal that is coming here, I use a multiplier. So after that, I put a multiplier. And I put here some value, say C sine omega t. And then I go here. And if I put a multiplier, what will it do to my first one? Sine square omega t. And sine square omega t would be what? I can write it as 1 minus by 2, right? So I get 1 minus cos 2 omega t by 2. So at the output, what are you getting? What will you get? You'll get the following. Half will give me A0 by 2. You'll get A0 by 2 plus all higher frequency components. Omega, 2 omega, 3 omega, 5 omega, all higher components. I'm going to get a DC when you multiply. And you'll get all higher components here. So what you do is, after this, you add a multiplier here. After this, add a multiplier, multiply it by sine omega t. Precise value of sine omega t. And then you will end up with a DC, A0t plus higher frequency components. And again, you sort of block, use a capacitor or whatever to block. So what it will do is, it will eliminate all the higher frequency, all the AC part here, and will allow only, use a capacitor or a filter. What I'm saying is, use a capacitor or a filter. So it will block all of that. On all you will get is A0 by 2. So you can almost get rid of the effects of the noise also, and recover A0 by 2, which is A0 here, which is related to the amplitude at which you are chopping. And that's the basis of, if you want to read more about it, so I've talked about chopper amplifier, and when you do all of this, that's the basis of what we call as a lock-in amplifier. If you go on the web, you'll find a very powerful technique which is used, which is called lock-in amplifier. You know, you sort of use a sine omega t which locks onto it and builds this here. Okay, so let's stop here. And next lecture, then we'll discuss our common emitter amplifier.